In this problem, we have ammonia, which enters a heat exchanger at steady state as a superheated vapor at 14 bar 60 degrees C. That's over here. And exits as a saturated liquid at 14 bar over here. The mass flow rate of ammonia is 450 kilograms per hour. We're also told that a separate stream of air enters the heat exchanger at 17 degrees C, 1 bar, and exits at 42 degrees C, 1 bar. So that's my exit, and here's my entrance. If we're allowed to ignore heat transfer to the surroundings and kinetic and potential energy effects, we want to determine the mass flow rate of air in kilograms per minute. So let's define what our control volume is. Our control volume is going to be containing our heat exchanger and contains both the air and ammonia channels. Now the air and the ammonia channels do not mix. So when we start to look at our mass rate equation, so the change in mass, we need to look at each of these channels individually. So the ammonia and the air, because they do not mix and they're separate. So we'll call the ammonia A. It's going to be equal to the mass flow rate of my inlet of my ammonia minus the mass flow rate of the outlet of my ammonia. Similarly with air, we'll call it dmr over dt. So the change of the mass of my air with respect to time is the sum of my inlet of my air minus the sum of the mass flow rate of the outlet of my air. Now, because we're working with steady state, these two values are going to go to 0. And each of these only have one inlet and one outlet. Let's call this state 1, this 2, this 3, and this 4. So this will simplify to 0 is equal to, this is ammonia. So ammonia is, my inlet is m dot 4. My outlet is m dot 3. Now for air, my inlet is equal to m dot 2. And my outlet is m dot 1. We can see that for each of the streams for air and ammonia, m dot 4 is equal to m dot 3. And we were given this, so we'll just call this m dot A. And for the other one, m dot 2 is equal to m dot 1. And we'll call this a mass flow rate m dot r. And we're trying to find that. So now let's move along to the energy equation, energy rate balance. So dE dt is equal to Q dot minus our work. And we have multiple inlets and multiple outlets of the control volume. So we can't simplify it, even though we can simplify the individual streams. So we're going to have to do the sum of my mass flow rates that are in my inlet times their enthalpies plus their kinetic energy term plus their potential energy term. And then we're going to have to subtract out the mass flow rate of all my exit. So times their enthalpy plus their velocities. Oops, this is E. Plus their potential energy term. And now's a good time to simplify this equation. We're at steady state, so this term's going to cancel out. We're told that we can ignore heat transfer to the surroundings. So even though this is a heat exchanger, the only heat that's happening is inside my control volume along this boundary. So it's not actually leaving the control volume. We're ignoring any stray heat effects or heat transfer outside of that control volume. So this can go to 0. We have no paddle. We're not outputting any work. we aren't receiving any work from, say, electricity or resistor, so this is going to go to 0. We're ignoring potential and kinetic energy effects, so these terms are going to go to 0, and our simplified expression is going to be the sum of my mass flow rates of the inlets times HI. So let's do that. Inlets are going to be m dot 4 H4, and then plus m dot 2 H2 for my air, and then minus m dot 3 H3 minus m dot 1 H1. So this one is air, this one is air, this one is ammonia, this one is ammonia. So a simplification we can make is we can substitute what we got for our mass rate balance into our energy rate balance. So 0 is equal to m dot A H4 plus m dot R H2 minus m dot A H3 minus m dot R H1. Now we can collect our masses, our mass flow rates. So 0 is equal to m dot A H4 minus H3, and then plus m dot R H2 minus H1. Solving for m dot R, we get m dot R is equal to m dot A H3 minus H4. We're moving this over to the other side, so we're switching our terms. Divided by, well, we're not subtracting that over, so these stay in the same order, H2 minus H1. Okay. So now we know m dot A. That's given from our problem description. We need to figure out what H1 is, what H2 is, what H3 is, and what H4 is. And we're given enough information. So if we start at H1 and H2, these are my air values. So my air values just rely on the temperature. So enthalpy is a function of temperature, and we need to make sure that we're using absolute temperature scales. So here we have H1 42 degrees C, which is equal to 315 K, and H2 is 17 degrees C, which is equal to 290 K. So what we can do is we can go to our air table and we can look up these two values. Let me get that. So here's my air table. I was using table A22, and we just have to look at our temperature and find the temperature that we're working with. So we're working with 290 Kelvin, and we're working with 315 Kelvin. So our enthalpy is just the corresponding entry, and we can make note of those two. So H1 is 315.27, and these are kilojoules per kilogram. And H2 is this 290.16. Now ammonia, we need to use different charts. Let's do our inlet H4 first. Our inlet starts as a superheated vapor. We were told that, so we go to our superheated table. On our superheated table, we need to know our pressure and we need to know our temperature. So 14 bar, 60 degrees C. We go to superheated ammonia. I already brought out the 14 bar. We go to 60 degrees C, and we look at what our enthalpy is. 1,542.89. Okay, and now we look at H3. So H3, it's a saturated liquid at 14 bar. So we go to our pressure table. With our pressure table, we go to 14 bar. We're a saturated liquid. So we're over here, 352.97. So now we have every piece of information we need to solve our problem. Let me write down what we have. M dot R is equal to our flow rate. Our flow rate is 450 kilogram per hour. Well, we need to put this, and we were asked to do this in kilograms per minute. So we'll just say 1 hour is 60 minutes. And then we continue on and we do, okay, this is H3. Minus H4. So this is going to be 1542.89. These are in kilojoules per kilogram. Now we're going to divide by H2 minus H1, so 290.16 minus 315.27. And when we put this in our calculator, we will get our answer. So we're going to have 450 divided by 60 times this difference right here. And then divided by this other difference. And we get that our mass flow rate of of air is 355.4. And let's do a quick unit check. Hours, kilogram, kilogram. This is kilojoule per kilogram. Kilojoule per kilogram. So the kilojoules cancel out, and we're left with a kilogram when we flip it, kilogram over a minute. So we get 355.4 kilograms per minute. And that is our flow rate for our mass flow rate for what air is.